Hello, my name is Emily Lewis and I'm a Structures and Cabin Safety Expert at EASA. And I will present an overview of the ongoing rulemaking and research activities related to helicopter ditching and water impacts. I will start by giving an overview of the Rulemaking Task 120, Phases 1 and 2, and then explain how these feed into the regular update of the Air Operations Rule, Rulemaking Task 392. I will then give a summary of the ongoing standards work related to ditching survival equipment. And finally, I will explain the ongoing research topics related to occupant survivability in the event of a capsize. So the overall safety aim is to avoid ditchings and water impacts in the first place. The reason a helicopter comes to enter the water, such as technical failures or human-factored related events, and preventing these is not the focus of this presentation. These are addressed by other EASA projects and activities. The rulemaking tasks described in the following slides focus on improving survivability in the event of an emergency over water and not preventing this emergency in the first place. So Rulemaking Task 120 addresses helicopter ditching and water impact occupant survivability and is a two-phase rulemaking activity. The first phase was related to a review and subsequent update of the certification specifications for initial airworthiness. In 2012, a rulemaking group was formed which included helicopter manufacturers, offshore operators, consultants, representatives for oil and gas, and also national authorities. The focus was on improving the occupant survivability following a ditching or water impact. Previous studies and a review of accident investigation reports highlighted that in otherwise survivable impacts, fatalities have occurred due to drowning. It was not considered feasible to define a water impact scenario to cover all possible events. Instead, by improving the ditching requirements in the CSs, the aspects of survivable water impacts are also implicitly addressed. The Phase 1 activity addressed all phases of a ditching or water impact, starting with the water entry phase and egress in the upright floating attitude, with a simplification of the requirements and improvement in survivability aspects. The capsize resistance requirements in the previous amendment of the CSs had little resemblance to actual sea conditions, therefore improvements to seakeeping were defined. The previous requirements also assumed that capsize would not occur. However, in many survivable water impacts, capsize and therefore flooding of the cabin is likely. For this reason, requirements to improve the means of escape underwater were developed. Finally, more robust flotation requirements were introduced to reduce the likelihood of the rotorcraft sinking. Another major update in Phase 1 of the Rulemaking Task 120 was the introduction of the 802 requirement for rotorcraft requiring the installation of emergency flotation systems without full ditching certification. Guidance is provided in the FAA ACMG 10, but there's no specific requirement in the CS. The aspects introduced for this requirement are the subset of the ditching requirements. The updated requirements were published in June 2018 in CS 27 and 29 Amendment 5. Post-capsize survivability features were proposed in the NPA, but not included in the CS update. These are the subject of an ongoing research project and are discussed later in this presentation. So Phase 1 covered the update to the certification specifications for initial airworthiness. Phase 2 of the rulemaking task looks at the potential to retroactively apply these requirements, or a subset of them, to the current fleet. The driving reason is that the timescale for an appreciable implementation of the Amendment 5 requirements in service is expected to be decades. Therefore, the safety improvements from Phase 1 will not be achieved for decades. Retroactive application of the Phase 1 requirement is also the subject of a safety recommendation addressed to EASA from the 2013 helicopter accident in the North Sea. In 2018, a rulemaking group was set up, which included helicopter manufacturers, offshore operators, helicopter associations and also national authorities. The MPA 2020-16 was published at the end of 2020 and the public consultation phase closed on 31st of May this year. 64 comments were received, which are currently under final internal review, and we aim to publish the EASA opinion shortly. I will present the key points of the MPA over the next few slides. These, of course, are subject to final review due to the feedback received from the public consultation. So together with the working group, the candidate requirements from Phase 1 were reviewed in detail to determine which requirements are not considered feasible to justify their applicability for retroactive implementation. One group of requirements was discarded as the amount of redesign or reconfiguration necessary for those Rotorcraft not already compliant renders the retroactive application of these requirements unfeasible or excessive. An example of this is the underwater exit minimum size. Another group of requirements was discarded as the safety improvement per helicopter type was considered limited, as the type is expected to be able to comply already or be very close to complying with the requirement. The additional burden of compliance demonstration far outweighs the potential safety improvement for the affected helicopter type. These requirements include the structural requirement 563. The final group of requirements were discarded because of the cost, complexity and potential weight penalty of the retroactive application was disproportionately large compared with the safety benefit that would be achieved to the entire fleet due to the small population of helicopters that would be affected. Full details of the discarded requirements can be found in the MPA 2020-16. I will now describe the options considered for the retroactive application. Option 1 was a comprehensive package of safety improvements which are considered to be feasible and pragmatic. The safety benefit from these improvements was qualitatively assessed as being low cost with medium positive safety benefit. The requirements in Option 1 include life raft remote deployment for CS-29 Rotorcraft, black and yellow markings for emergency controls if they need to be operated underwater. The effort requirement to open each underwater emergency escape route must not be exceptional. Life preservers, if not constant wear, must be within easy reach of each seated occupant. The substantiated sea conditions for capsize resistance must be published in the Rotorcraft flight manual so that the operators and flight crew are aware. The life raft retaining lines must be of a suitable length to prevent damage to the life raft or putting the life raft in a dangerous position. Automatic illumination of underwater emergency exits, and also an improved ratio of passengers to underwater emergency exits. So 1 pair of exits for every 4 passengers. The idea is that nobody will be worse than second out in the event of a capsize. Option 2 covers the robustness of the emergency flotation system in the event of a water impact. The aim of this option is to introduce practicable design changes that will minimise the effects of a water impact on the EFS based on lessons learned and today's best practices. TC and STC holders should propose suitable criteria to assess the practicality of the considered design changes and provide justification of their subsequent classification. Design changes that are considered practicable should then be implemented in production. The intention is to improve survivability in the event of a water impact by implementing straightforward design changes. For example, modifying the location or orientation of EFS components, the use of redundancy, flexible hoses, and avoid passing pipes, hoses, or electrical wiring through bulkheads that could act as a guillotine when the rotorcraft structure is subjected to the water impact loads. A cost-benefit analysis was carried out for this option, which resulted positive for in-production cut-in. The full retrofit option was discarded, as it would not be feasible to retroactively implement this requirement to in-service helicopters, due to the significant number of different configurations and also the extensive work that could be necessary to disinstall and then reinstall other non-related equipment to perform the design change. Option 3 considers automatic deployment of the EFS. So for CS27 Rotorcraft, the stowed EFS must automatically deploy following water entry, providing that it is armed. This is usually with water immersion switches. For CS27 Category A and CS29 Rotorcraft, this automatic deployment must not rely on any pilot action during the flight. This requirement can be met by the use of an automatic arming system or by having no restriction in the EFS being armed, so that it's always armed in flight. Mandating only the auto-deployment following water entry would not provide a significant survivability improvement in the event that the pilot is unable to arm the system. Some rotorcraft in operation already fully comply with this requirement. However, it is acknowledged for those types not already compliant, developing an auto-arm system or substantiating no restrictions with armed EFS is complex and costly. The cost-benefit analysis did result positive for full retroactive implementation of this requirement. A re-evaluation considering the benefits from auto-deploy and no pilot action requirements separately also resulted positive. The final option reviewed the irregular wave testing for the capsize resistance demonstration. This irregular wave criteria offers a more realistic measure of the likely actual performance of a ditched helicopter compared to the previous CS requirements indicating testing in regular waves. The cost-benefit analysis resulted negative for this option for both production cut-in and full retroactive implementation and was therefore discarded. So to summarise the Rulemaking Task 120, Phase 1 resulted in an update to CS27 and CS29 at Amendment 5 for initial airworthiness. Phase 2 considered the feasibility of retroactively implementing a subset of these requirements with an update of Part 26 and CS26. The three options proposed were the holistic safety improvements, a design review of the robustness of the EFS in the event of a water impact, and auto-deployment without pilot action. The 64 comments received are under final review, and the opinion is expected to be published shortly. The Rulemaking Task 120 activity also feeds into the next regular update of the Air Ops rules, Rulemaking Task 392. This is to ensure consistency of the cabin safety elements between Rulemaking Task 120 output and the SPA-HOFO rules. The items under review include survival suits and EBS, ELT installations, underwater escape egress routes, and the ease to identify the rotorcraft visually in case of a capsize by chevrons on the underside, for example. Following conclusion of the rulemaking process, including public consultation, the Air Ops rules are expected to be updated. Over the next slides, I will provide an overview of the ongoing work related to the ETSOS for ditching survival equipment. The MPA 2016-01 from Phase 1 of the Rulemaking Task 120 recommended a review of the helicopter ditching survival equipment ETSOs. This included recommendations for constant wear immersion suits, life jackets and EBS, such as self-righting capability, different levels of thermal insulation dependent on the seawater temperature, and the development of an EBS ETSO. For life rafts, an update was recommended to include improved puncture resistance, compatibility with remote deployment, provisions for 2 retaining lines, and testing requirements for deployment, including underwater deployment. ASD-STAN Working Group 2 in the cabin domain is currently working on standards to address these issues for ditching survival equipment. In addition to considering the Rulemaking Task 120 recommendations, these standards aim to significantly enhance survivability in the event of a ditching or survival water impact. The EBS ETSO has been published, and an update to CS ETSO to refer to the group of standards when issued is expected at a future amendment. I will now present the ongoing research activities related to improving occupant survivability in the event of a capsize or survivable water impact. The MPA 2016-01 from Phase 1 of the Rulemaking Task 120 included post-capsize survivability features that were not included in the update of CS 27 and 29. These are the subject of this research project, New Flotation Systems. The research project received funding from the European Union's Horizon 2020 programme and was awarded to DART Aerospace. The objective is to provide answers to technical issues regarding the feasibility of providing a step change in occupant survivability following capsize of a helicopter through the introduction of an air pocket scheme, utilising flotation units mounted high up on the helicopter fuselage. The project started in June last year and will be completed in June 2023. So helicopters have a high centre of gravity, leading to challenges in providing the necessary capsize resistance in all emergency situations. Even considering the updated CS requirements for capsize resistance, capsize cannot fully be prevented, especially in situations beyond the demonstrated entry envelope. Many accidents have occurred in which helicopters survive such a water impact, only to then drown due to their inability to escape from the capsized helicopter sufficiently quickly. The CS update also included requirements to improve the ease and speed of occupant escape from a flooded cabin. However, effects such as cold shock and disorientation mean that there's a practical limit to how quickly helicopter occupants can make an escape. Human breath-holding ability in the worst case is only an order of seconds. This situation has been recognised for many years, and extensive research has been directed at identifying and refining a solution. The proposed solution aims at providing a capsized floating attitude with an appreciable portion of the passenger cabin remaining above the waterline, the so-called air pocket. Helicopter occupants would easily find this unsubmerged portion of the cabin, enabling them to breathe and survive within the helicopter before finding an escape route and entering the life rafts. The following aspects have already been investigated, including a validation of the feasibility of the solution by wave tank testing and human subject trials. Technical issues were highlighted which require further investigation, and for this reason, this requirement was not introduced into the CS 27 and 29 update. These technical issues are addressed by this research project. The technical issues are summarised as follows. Inadvertent deployment of the high-mounted EFS could lead to interference with the main rotor. This has catastrophic consequences, and therefore the probability of inadvertent deployment must be extremely improbable. The installation of high-mounted EFS could lead to adverse aerodynamic effects impacting performance, loads and handling qualities. This will be evaluated and minimised. The location of the EFS is close to the hot engine exhaust. Degradation of the stowed EFS due to this high temperature must be prevented. Damage of the EFS due to main rotor debris at water impact or capsize is also to be prevented. And finally, overall integration issues must be resolved, including potential interaction with other external equipment, maintenance, and continued functionality of the emergency exits. The economic impact will also be assessed. The conclusion of this research may indicate that a rulemaking task should be launched. This could potentially impact CS27 and CS29, introducing new certification requirements for initial airworthiness. The special condition VTOL means of compliance is based on the Rotorcraft certification requirements and may also need to be reviewed. This research task may also introduce new aspects into the air ops rules. So other research is also ongoing regarding helicopter underwater escape. As previously mentioned, there is an incompatibility between human breath hold capability and the time required to escape a capsized helicopter. A safety recommendation addressed to EASA from the 2013 helicopter accident in the North Sea recommended that a research project is carried out to provide realistic data relating to the evacuation and survivability of occupants in the event of a helicopter underwater evacuation. The first EASA research project on this topic was to carry out an initial review into the nature of the research that could be envisaged to answer this safety recommendation. This project was performed by the UK CAA. The first task was to perform an analysis of the currently available information. The shortfalls in this data were identified and future research activities proposed to address these shortfalls. The research project was completed in November last year, and the comprehensive report is published on the EASA website. This initial research project identified 3 high-potential safety benefit future projects: investigation into the forces required to jettison push-out emergency exits, underwater escape from the cabin with a full complement of passengers, and passengers training and fidelity. Of these 3 potential projects, 2 have been selected for a subsequent research project funded by the European Union Horizon Programme. The call for tenders is open until 19th of November this year. So Task 1, Forces required to jettison the underwater push-out exits, aims to evaluate the influence of being underwater on the required force and determine the maximum force that a person could apply to the exit. An appropriate maximum force can then be established, confirming the current AMC material or proposing a future revision. Task 2, Underwater escape with a full complement of passengers, aims to quantify the escape process and determine if the expected 60-second escape time is achievable. This will validate the current requirements or lead to a proposed update. If regulatory action is considered necessary based on the conclusion of this project, the subsequent rulemaking task could consider updates to CS27 and 29, the Air Ops rules, the ETSO for ditching survival equipment, and also the special condition VTOL means of compliance. In addition to EASA rulemaking activities, Task 2 aims to fully answer the safety recommendation. So to summarise the research activities, the ongoing new flotation system project is investigating the technical issues highlighted during previous research regarding the feasibility of installing a high-mounted emergency flotation system in order to provide an air pocket for the occupants in the event of a capsize. The first helicopter underwater escape research involved a review into the research that could be envisaged to better quantify the characteristics of helicopter underwater evacuation. This research identified 3 high-potential safety benefit projects. 2 of these projects, the forces required to jettison underwater exits and underwater escape from a cabin with a full complement of passengers, are selected for the second helicopter underwater escape research project. The call for tenders is open till 19th of November. So during this presentation, I have described the ongoing rulemaking and research activities related to helicopter ditching and water impact, occupant survivability. The Rulemaking Task 120, started in 2012, led to an update of the CS27 and 29 in June 2018 for initial airworthiness. Phase 2 of this activity regards the feasibility of retroactive application of a subset of these requirements, proposed an update to Part 26 and CS26. The final review of comments received during public consultation is ongoing. The Rulemaking Task 120 conclusions are also being reviewed in the regular update of the Air Ops rules to ensure consistency of the cabin safety aspects. Rulemaking Task 120 also recommended review of the ETSOS for ditching survival equipment standards. Post-capsize survivability features proposed during Phase 1 of the rulemaking task were not included in the CS update. This is the subject of an ongoing research project investigating the technical challenges of providing an air pocket in the event of a capsize with the introduction of a high-mounted EFS. In addition, the first helicopter underwater escape research was completed last year, recommending 3 tasks, 2 of which have been selected for the second research project. These aim to address the safety recommendation and may also result in future rulemaking activities to improve survivability in the event of a capsize. Thank you for your attention.